Our speaker this evening was formerly the Vice President of Mellanox and the CTO of Voltaire. Please welcome the current CTO and founder of Iguazio, Yaron Haviv.
Thank you. So what I'm going to speak today about is serverless and how it's being used in big data and AI use cases. We'll do some demos. Beyond my role in iguazio, I'm also pretty active. I'm a blogger. You can read, I'm writing examples, Kubernetes, big data. And I'm also working in the CNCF Cloud Native Foundation on the standardization of serverless across vendors. Something that I assume many of you would like over time, so you're not sort of locked into one vendor. And I'm going to start by defining what serverless, how it's used, and how specifically it's being used in big data and analytic use cases. Okay. Okay, so let's start by talking about the problem. I assume you guys are into big data and you've looked into those challenges of starting to build solutions that it's easy to do, and Spark. And then over time it evolved because there were new tools and you needed streaming and you needed some messaging, maybe caching like Redis. And over time it evolved even further because you need some machine learning or deep learning. And maybe Spark is not enough, and then you need Presto and other solutions. So all that became pretty complicated and very hard to manage because, for example, you cannot have one scheduler like Yarn to manage all those things. So things like Redis or TensorFlow or others don't really work in such a Hadoop environment. And from having a data lake, which is more of a batch processing, we now need something which is a lot more agile. And sort of the new stack that we see forming. So before that, we see that everyone is talking about how to deliver those things in a more agile manner. And I'm taking an example from two guys, Satya from Microsoft and Andy. That's a picture just from yesterday. I was in Amazon event from Andy's keynote. And you see that the key point that they are talking about how to address those issues are around serverless functionality. And serverless functionality is becoming very dominant, and also Amazon just announced a serverless database, which is an interesting approach. So serverless has usually is a stateless thing, and database is a stateful thing. But we're seeing the notion of this serverless, which essentially we'll talk about the definition, is something that you don't really need to manage the infrastructure. And the other areas that are the focus of the cloud providers are around data and artificial intelligence. So those three pillars of data services, or managed data services, artificial intelligence and machine learning, and serverless are sort of the driving forces to build all the new use cases to drive modern businesses. And one of the ways to build all those, if you don't just want to go to a specific cloud provider, is essentially to build a stack that looks like this. So there is a traditional stack that you guys are probably familiar with, Hadoop and Spark, etc. But that doesn't hold all those applications that we need to serve. Again, there are deep learning and machine learning services. There's the glue logic that needs to happen. There's real-time and serving and dashboards that need to happen. So now we're looking into scenarios where we have a generic sort of scheduler or orchestration layer in the form of Kubernetes. It's so important that even yesterday, Amazon announced support for Kubernetes. If you've followed that news, Amazon supports it, Oracle supports it, Google, and Azure. So all the major cloud providers, and you can just download it and install it on your own. Underneath, we need mainly three forms of data. So this we categorize all the data that we have. Instead, there is unstructured things like files, Parquet, etc. And that could sit either in HDFS, but also in things like S3, object store, shared file system. Another thing which is very important, especially when you're starting to go into real-time analytics and structured data, is structured data. So like you need to count something, so you need to store it in a table in a record. You have a list of customers that you need to use them for some data. You don't want to scan all the time. which is what we're doing with unstructured data. So we need structured data, and here you have things like Cassandra or Redis, or if you're in the cloud, things like DynamoDB or Spanner, and obviously also the iguazio platform provides those. And the last form is streaming or message queuing. It's a way to pass messages from one way to another in a sort of durable way and in a very scalable way. So here you have solutions like Kinesis and Amazon or Kafka, which is an open source framework. So then we have sort of the substrate, the basic of having a data, having an orchestration layer that can run different workloads on top of it. And then on top of those, we can divide the services to two forms of services. There are things that have their own framework. If you think about Spark, it manages its own cluster and its own communication and shuffling. So that would be a microservice, or say for TensorFlow in the context of learning. It needs to distribute the learning job among a bunch of workers, and it's handling it by itself. Then for other tools like Python and Pandas and Anaconda that you may have used. But there are many other cases where you just need some glue logic to handle an event, and we'll see some things to do inferencing, where you get a text and you need to analyze it, and maybe you have some voice and you want to convert it to text, or you want to serve a website or a dashboard. All those things are better served with the notion of functions and serverless. Any questions? Or
just one request that you hold the mic closer to you.
Okay.
Yes. There you go. Thank you.
So what is serverless? Okay, and I took from some of our paperwork on the CNCF quote. Not everyone agrees in a standardization logic that you probably can understand. But the generic concept of serverless is that we create functions, and those functions are wrapped typically in a container. There's something which is called invoker, which gets the trigger, gets an event, and calls this function callback within the function. You could have those elastically, so you could have 1, you could have 0. If you're not using it, it just disappears. And if you have a lot of usage, it scales automatically. So it's very nice that you don't need to think about scaling the function. Another key element is the event sources. So those functions are usually triggered from something, whether it's a stream, an HTTP request, a message queue, an event of a platform like Amazon, where you throw an image into an S3 bucket, and that triggers a function that, for example, can allow you to convert it to a thumbnail. So those are the two key things that you have, triggers and functions, and there is a controller that can essentially monitor the triggers and form the function. Okay? And underneath that, you have platform services. So for example, if you're in a cloud provider, the cloud provider will provide identity management, security, logging, etc. So that's the general idea. And the notion of serverless, the reason it's called serverless is because it's serverless, meaning you don't need to think about servers, you need to focus on your application, and I'll show some demos how essentially you don't need to think, not even about containers or any of that stuff. Just think about code, run it, debug it, and then let the system go and deploy wherever you want. So different use cases that we have for serverless could vary. One is, for example, real-time analytics. So think you're getting, traditionally you think about it in big data, you're saying, okay, we need stream processing. We'll take Storm, we'll take some of those things. But some of those things are limited because they're limited to an individual function, individual language, for example, Java, which may not have all the libraries that you could find in Python or in Go or in another language. It's limited because it doesn't have all this auto-elasticity and all this richness of debugging and other tooling that you get from a generic platform like serverless. So essentially you could use serverless function as a mechanism to do stream processing. And we'll see that it requires a little more work. So you get those events. Sometimes you need to correlate the events with existing data that you have, some tables, some counters, some caches, and maybe if you have you found something, you need to notify another service or get more details from another service. So this is the generic case of real-time analytics. Another use case could be ETL, or data movement. So let's assume I can run a function that listens on an object bucket, on a stream, on a table. And every time there is a change in the data source, we'll actually take that and throw it to a secondary data source. So we can implement something like an ETL or a backup or a DR, or just take from one data, transform, filter, take only the rows that we need, and throw it to the other side. And again, we don't need to think about elasticity, scaling. We just write functions, put them listening on an individual data source, and push the data into the destination. Other use cases, which are typically not used in big data, are more the interactive ones, like just serving on the website. Or in the future, everyone is speaking about bots, Alexa skills, and all those things. So you write a function that will get the text or the voice or just the UI request, HTTP request, take some data, work with some backend services, and respond with the HTTP content or with the voice content. Another thing that you'll see is serverless is also used for edge computing. Amazon has an SDK with Greengrass. Azure also has something like that, which essentially you can run, compile, and debug a function in the cloud, and then publish it into an edge device somewhere that may run with a Raspberry Pi or even something cheaper than that. And this guy will get sensors, local sensors, will run some functionality and throw the results into the cloud after filtering the data. Okay, so those are the main use cases. I assume you can find more use cases, but those are the things that we sampled here. Now, function invocations, if you go to Amazon or to, I think Amazon has the richest set. Actually, we have in nuclio more capabilities, and I'll talk about it. The first model is essentially a request-reply model, like a web server. So you have an HTTP API gateway, you'll get an HTTP request, throw it into the function responds, and that's it. The second model is something called asynchronous model. That means that we get an event that goes to an exchange or a message queue, and then one of the functions picks up data and processes it. There is no ordering. So, for example, this function can take the first guy, the first message, the other one, the third. And if it fails, someone else will take another message. They may be processed out of order. So that's the notion of asynchronous messages. Another thing that's used quite a bit in big data is the notion of streaming, where you, for example, take Kafka, you partition Kafka to multiple partitions, and each one of those partitions have to be processed in order. So that means that only one guy can work on the same partition. It needs to do things like checkpointing. If it fails, it needs to recover from exactly the same point. There are other more complicated things like exactly one semantics, which I won't go into. But that's a more complicated use case. And the fourth use case, which is not supported by most of the platforms, is more of a master worker scenario, like something like a batch processing or a Spark. You throw in a job that's distributed to a bunch of slaves, you process it, finish, and return it to work. Same model like Spark, if you're familiar with Spark. So today, Amazon supports those three. Most of the open frameworks support only the first model. We looked into OpenFaaS or other solutions that are only supporting HTTP. Some use sort of Kafka with a single partition, which is very limited and not really useful for big data use cases. The only project, open source project that supports all those four use cases is Nuclio, which we're going to go into in a minute. Okay. If you think about how serverless functions work, why it's so nice, is that you have an automated development workflow. If you're familiar with the notion of CI/CD, continuous integration, and continuous development, then essentially you have a code, we have a specification that defines things about the code like dependencies on packages, environment variables, other preferences. The minute that you push save on your function, you run the process of building that function, generating an artifact. Usually the artifact is a Docker container. That Docker container contains your code compiled with all the definitions around the dependencies and environment variables, and then you deploy it on a cluster. Okay, and then there is a controller that's in charge of deploying that on a cluster, whether it's a cloud cluster, whether it's an IoT device, or Kubernetes cluster. Okay? And another interesting thing is that you can have this shared this artifact repository, this Docker repository, is a shared entity, so you can generate a function, store it once, and then deploy it in multiple places. And that's something that we do in Nuclio. It's not really applicable to Lambda. Lambdas are absolute for this is invisible in Lambda and other frameworks. In Nuclio, you can actually do it in 2 steps. You do it in 1 step, where you could choose to deploy wherever you want. Okay, so I mentioned something called Nuclio, which is very new. This open source project. Iguazio is a company that essentially develops a data platform very similar to what Amazon does, just for on-prem or devices. And we have our own something called like stored procedures in our system that was very similar to serverless. So at a certain point, we said, why don't we just open source that technology and we form a project? We redesigned it and form a project called Nuclio. It's getting a lot of momentum. Right now, it's about 1,000 stores in GitHub, and it was just launched a couple of months ago. There are major software developer and software companies that want to adopt it and join us in this development. And the reason it's speaking up so quickly is because it's extremely fast, and it has a lot of functionality that you will not find in any other serverless framework. So one of the examples is this framework. You can write functions, and it will be able to run 400,000 events per second on a single process. What Amazon Lambda does is about between 1,000 to 2,000.
What is the event?
Sorry?
What is event?
Event is just like you get an HTTP request, you respond hello world, for example. You can do about 400,000 hello words. Or if you take OpenWhisk or OpenFast or all those other open source frameworks, they'll go about 1,000 to 2,000. And Lambda does it less depending on the situation. So when you're doing high-speed, real-time analytics or stream processing, 100 times faster could be pretty interesting. You can also use less processes, less CPU, and less memory. The reason that it's so fast is because it's essentially creating a real-time operating system around the function and not just invoking or executing the process every time again and again. And it has other nice concepts, like it has event listeners that eventually push the event into the function using exactly the same signature regardless of the event. So if you're working with Lambda today and you choose Kinesis or HTTP, you have to write the function in a different way. In Nuclio, you write the function only once in one way, and today it's a little blurry. It supports Kafka, Kinesis, RabbitMQ, NAS, HTTP, probably missed the thing, and iguazio plus obviously. So you can write the function once, you could test it with HTTP as a triggering mechanism, deploy it on a local cluster with Kafka, or deploy it in Amazon with Kinesis without recompiling the function. It has other interesting capabilities like pluggable data bindings. One of the biggest challenges in serverless, let's assume you want to access a table from serverless function, you have to do it in global variables, and it's very security, it's risky in terms of security because you have to put your credentials. If you have errors or failures during the connection of the database, you don't see that, you cannot log that, so it's very tricky. So what Azure did in their function is the ability to have something called data binding, to through policy define which tables you want to see from the function, and we've adopted this notion. The other interesting thing is essentially it has a platform abstraction layer, so it can run across Docker containers, Kubernetes cluster, or standalone. And it has a lot of other interesting tools like CLIs and user interface, which I'll use in the demo, and it will integrate with different blogging and repositories So for example, you're using Google Cloud, it's integrated with GKE, and you can just use all those services from Google Cloud, and we're working on the same capabilities with the either Kubernetes service and Amazon just announced their Kubernetes service. And there are you'll find a bunch of articles in different publications about nuclio and all those unique capabilities that I mentioned. So the advantage is it essentially works with any data source. So if you're using Lambda, you're really limited to Kinesis as your streaming engine. Here you can choose your streaming engine or your data engine the way you want. You can actually develop the function using your laptop and then just publish it and use it in the cloud or on a cluster or on an IoT device. It has extremely high performance. Again, you can run and test anywhere you want. You can test in one place and deploy in a different place. And it's has a simple and very fast and secure data integration. This is just a benchmark to show 400,000 invocations per second, but you'll get probably 1,000 or 2,000 in most platforms. This is the function. One of the unique things that we've done in order to address stream processing, because serverless is not necessarily stream processing, because of this issue of distributing workloads or shards or partitions of streaming among different functions. So for nuclio, we have a service that knows how to dynamically distribute the shard of the streaming or jobs or tasks among the function. And that's something that's also very unique and allows nuclio to act like a stream processing engine beyond just a generic serverless framework. And still not in the upstream code, but it's going to be there in a few weeks. Any questions on that? You can ask me afterwards. I'll open for questions. So if we're looking at the big data scenario, and especially more something that works with active data set or real-time analytics, then we have several use cases. The first thing we need to do is ingestion. Ingestion, we get data from either external data sources or internal data sources, maybe a database that has changes or an ETL job. All those data sets that feed into the system, the first thing we need to do is potentially structure the data, filter the data. Maybe already in the ingestion portion, we can identify alerts. For example, we have a car, and send us an notification to a JSON, has a problem. We don't really need to store that in the stream or in data and then alert. We can immediately, when we identify that, go and alert. We can take the data, read data from a database, compare it, or run even AI inferencing logic, and respond based on that. Once we store the data, again, those serverless functions are stateless, so we have to store all the data in those three different forms of structured, unstructured, and streaming data. Here, now dashboards can read. We don't need to form pipelines. The traditional notion in big data that we have to form pipelines. The new form, which allows more real-time and more interactive analytics, is that everything works in parallel. So we can ingest data. At the same time, we have dashboards that just read data that is up to date. We may want to analyze the data, because those tables are up to date with the ingested data, and we can just run Spark or TensorFlow or any other framework to analyze the data that we have. In some cases, we need access to external data, like data from a weather source, data that we store on S3 buckets, so we can run functions that import and export data into this working data set. Okay? So you have one continuous workflow where essentially what we use as building blocks is a set of data services for structured, unstructured streaming data, a set of serverless functions, and analytic frameworks like Spark. So that simplifies our entire architecture because then we can take those data services, layer some Kubernetes or cluster management tool on top of it, and all of those things are microservices. Some of them are packaged, through Helm charts or package management like Spark, and some of them are essentially automatically packed with the build using serverless technologies. Okay? And that allows us much more agility. Now, if, for example, we decided we want to change the UI, the user interface, because it's a microservice, we go and exchange the version of the function, and the serverless framework will automatically pre-build and convert the version of the function into the new version. Okay? And if for some reason we don't like this change, we can always revert to a previous version, because serverless is always version, or most applications are version. Okay? And that's the advantage of using more of a cloud-native technologies than some of those technologies that we're used to from the Java world. And what really allows you is much better productivity, much faster insight, because everything is continuous. Infrastructure in this case is invisible, and we'll see that, and is lower cost. This is an example of a function which does sentiment analysis. You can see only about 10 lines of code. One of the interesting capabilities when you're building those functions, you have dependencies. You need some libraries. This is an example of usage of an existing sentiment analysis library called behavior sentiments. So we need to essentially import that function or install that function in the Docker containers that contain the function. So essentially we can mark and create declarations that tell us go and install this dependency. And this is, for example, you're using Lambda, that will be much more complicated. You need to create a zip file and rendering and all that. In nuclio, we try to make things simple. You just tell us which are the dependency, and then you write the function. The function has a signature of context in that. The context provides you a lot of interesting things like logging, and levels of logging and structuring. And the event is where you actually get the context of the data that triggers the function. The event, for example, has a body. You can see where it's loading the body of the event, and then we're logging, we're just printing the data, we're running the scoring or the inferencing of that text, and we return the score at the end. So we created something that we went to Google, we found a library that does sentiment analysis, we download, we clean it a bit, and now we have a working data set. Okay, now just so you know, it's not really complicated to install. The only thing you need to do is run this command line. You go to the website, you'll see that, you don't need to remember. With a single command line. Because again, we said we have deployment model with Docker, and we have deployment model with Kubernetes, which is more comprehensive with clustering and CLI. If you want to use only the standalone version, that's the only thing you need to do. No installations, nothing. And then just go to this port using a browser, and you have a user interface. This is once you type this Docker command, and you went to the HTTP, the URL. This is what you're going to get. And what you can see is, let's go back to this sentiment analysis example. Okay. We see the same code that I mentioned. We can go in. We can look at the configuration of the function. There's a lot of metadata. We haven't exposed everything for the UI. This UI essentially generates a YAML file that could be edited. So you could go to the documentation and you'll see all the details. You can specify like the amount of CPU and memory required. But the key things are like you can create a description and a name and give it labels. So then you can search for functions using Kubernetes tools. You can have environment variables. You can have build instructions. You can even specify the base image. Well, we really use this base image, for example, in TensorFlow, which have a lot of dependencies. We just use a different Docker base image. And then you see those dependencies of things that I need to install. And I can also use data binding to still have some gaps on the implementation. And then on the triggers, I could select which triggers I want to use. For example, let's assume I want to trigger from Kafka, I don't need to work too hard. I don't need to understand SDKs. I just need to say I need Kafka. Okay, and I need to specify. We don't really see all the details now to the screen, but I can go and specify the parameters like the IP address of the Kafka, the topic, etc. which I want to listen on. And I could listen on multiple events. That's a nice thing because it's event driven. I can have one function that listens on RabbitMQ and Kafka and HTTP and choose how I want to use it. So going back to the code, the only thing I need to do is deploy. This deploy takes the code, compiles it, builds the artifact, the Docker images, okay, and you see it's finished, and now it's listening in a certain port. And I could probably need a better. Let's give it a try. Okay, so I think it's a positive statement that I love. So you see the simplicity. I didn't need to think about Docker containers, Docker files, not to mention if you're working with Java classes and Hadoop deployments and all that. I just wrote my code, push deploy, compiled, and then I used the built-in tools to test it. But I can also use Postman or any other tools because it's an endpoint. Actually see the address of that function here. Okay, so very easy to go and build complicated things. Let's try something else. Let's assume I'm getting data and I'm a bank or regulated entity. I want to check if this data has social security numbers or credit card numbers. Okay. So what I need to do is every time the file lands, I want to scan the file and look for a certain regular expression pattern. Okay, so this is now, the previous one was implemented in Go, in Python. Python is not as high performance as Go, so I can just create a new function. You see the function generates the regular expression parameters. It will get the event. It has a logging. So I can log under debug. So that means that in normal operation, I actually won't see those events, those debug logs. Only if I change the level of the debugging, I will see those debug logs. And that's very powerful. That's capabilities that you don't get with Amazon Lambda, because Lambda just logs everything. So either you have graphic performance or you have details about your function. With this architecture, again, you can put a lot of debug logs, a lot of information. At runtime, decide if you want to turn it into a debug mode or not, and you can even do that for invocation. So you can have the system running on error level, but do specific tests on debug level, and not pollute the production system. So. It's just checking a pattern, so it's not that sophisticated, but you can take the exercise of creating a more sophisticated function, and you see that it contains a credit card number. So you see, again, very easy to create versatile examples, different languages. Okay, there's also shell processor. Next week we're going to add JavaScript. Java is still not supported. I hope towards the end of the year. Again, you have all those things. Now, if I want to debug mode, see that I have a debug message. Okay, that was that. Now a warning message, so I can control which messages, which log events I want to see. I don't have to see them. And I can continue and have more examples here. You know, this is a face recognition example using the Azure API. All those examples are also in the website, in the GitHub. You'll see under examples. It's also linked from the nuclio website. So this is using the Azure Face Recognition API, it takes an image and returns the classification, tells us a boy or a girl, has glasses, etc. There's a more complex TensorFlow example, because you think TensorFlow is something heavy, and it requires a lot of dependencies and computation. You can actually run TensorFlow as a function in nuclio. It requires a bit more work on the configuration, because it has slightly different dependencies, like we need a different image, sort of a Ubuntu Jesse image in this case, and it has also other dependencies around TensorFlow and NumPy. But again, the code can go and do even such complicated things, accept the content, analyze it, and return the classification of the image. So that's in general. We can continue on and on with all those different examples, but you sort of got the idea that I don't need to think about deployment of servers. I don't need to think about scaling out, scaling down of services, build services. Everything is versioned. Disconnected, but see, I went to the CLI on the back end, and I can see all my functions, their version. I can search them based on labels, and this is using built-in Kubernetes capabilities. Okay, so so we got sort of the basics. So I'll show you some other use cases that we use nuclio in real customer scenarios. So this is an example of the video surveillance. Okay. So what we do, we ingest the pictures into the system using object APIs like S3. Those object API inserts generate triggers. So the functions can actually listen on those triggers that the new object was created. Those triggers can trigger two functions in parallel. So we always think in big data about pipelines. So we do one thing, and then we do the other thing, then the third thing, and then it becomes slow. But with those mechanisms, you don't have to wait. It has one function that analyzes the JPEG headers of the picture and determines like geolocation and other metadata of the picture, and another function that uses TensorFlow and essentially gets all the classification of the image. And in parallel, we can have Spark that looks at that data set and does other things with the metadata that we created from the picture classification.
It doesn't matter. Only one of them is slow, and it doesn't matter if you do it sequentially or in parallel. It's still limited by the slowest function out of them.
No.
So the prediction, if let's say TensorFlow is slow, 10 times slower than
the why no? And I'll maybe we'll see that in the other example. Because sometimes this detection is not a critical step, because in parallel you have dashboards that, for example, see data. If some of the content is delayed, this may not be critical. I can show you some other examples. Because sometimes the learning takes 5 minutes, and you get any information, then after 2 seconds you get already information about the learning, critical information. The dashboard wants to see that, and maybe it takes 5 minutes to figure out an anomaly, and you can add in another field. It's very important in those cases to actually use structured data, because what you do is every function will update a different column for that problem. Okay, but you don't necessarily have to wait, and I think that's critical thing that not all of our customers sort of adjust immediately, is that if you're starting to work in parallel in real time, you have dashboards and you have actions and triggers. Some triggers don't really, you can immediately act on them. You don't have to wait forever. This is another example of fleet management, and you can take the same thing for automotive and connected cars and sensor and IoT. Again, you get triggers. Those triggers, you have to, when you do the enrichment and take the decision, you have to add other external data. Like in this case, weather information, road information. So we can have a service, a microservice that imports those external data sets, like weather and other, into the table internally. We can have this data being correlated using a function, essentially taking the event data, taking external data, doing some decision making, if it needs an alert, it alerts immediately. If not, then you just store the data here, and the machine learning will happen in delay. It doesn't necessarily have to create something immediately, because some triggers could happen in real time. Like we've seen the car is going to crash, and maybe we already determined that, and we act on it immediately. And maybe the fuel consumption average could be something that calculates slower, and after 5 minutes, I'll get a picture of that. And dashboards could also be other functions that essentially when a JSON call from the Angular client arrives, this function will go and probe in the data, prepare a JSON response and response to the client. And this is how it looks like in real production. So we have all the enriched events, we have geolocation maps with all this information that was gathered continuously. We have other analytics, so think about like a real-time tableau that feeds from a real-time data set and through the video to the system. So if we look at a similar use case and I break it through different models, so the first thing I get is state and the events of the cars. When I'm getting information from the car, I have to do a few things. First thing, I want to see what was the previous state of the car. Because if it's showing an alert, but maybe a minute ago it showed an alert, again, that means that probably it's not a new alert. I don't need to really do anything with that. So every time I get an event, I have to essentially enrich that event and create a denormalized event, or what is called an enriched feature vector, that contains information like previous state, like time series aggregation of that state. Let's assume I'm a market trader and I get information about the market. It doesn't tell me much if I don't know what was the trend in the last hour. So we have to embed statistical or historical data. We need potentially secondary tables like driver tables or road information tables. And here we now form this enriched feature vector that contains all the additional metadata that we'll need for decisions. And then we can do simple decisions like, okay, the state of the car changed, we need to alert another function that will do something more sophisticated. Or maybe we've identified that the road allowed speed is 60 miles per hour, and this guy is driving 100 miles per hour. We would compare two different data sets, the event data set and external data set, and we can trigger a violation on that driver.
What do you do with this violation?
We'll give you a ticket. Depends on.
Without zero, it's difficult to give a ticket.
No, again, this is an example. It's not really giving a ticket. It's tagging the driver, and don't worry. Another thing that you can do geo-aggregation is on maps. So every time we see the car moving, we update the geo hash table. And then the map that looks at those cars will get real-time updates of those changes. So we don't throw the data in a Kafka stream and then to a data lake and then analyze it, and then an hour later we have an updated map. We actually have a real-time update on a map because in the context of the event, we already do operations like plus or minus on cells in the geomap location. Another thing that we do, we take this enriched data set and fit it into a stream. And that stream can be read by something like Spark and do longer-term calculation, which is what I prefer doing when you ask. All those things could happen in real time. And this thing could happen in a 5 minutes delay, nothing happened. So we don't necessarily need pipelines. Some decisions can happen in real time. Okay. This is the code for that function, but probably not clear enough. But all the things that I demonstrated here is 60 lines of code. All this complex processing that you've seen. With that, I'd like Blossom now to show you this thing live with some emulation. So what we have in this example is similar to what I described before with the functions. We have here an emulator that generates all the information of the cars. We have a nuclio function that intercepts those JSON structures and works against the database to update all those different data sets. We have Spark that looks at the same data set, so we'll see in a minute. and we have live dashboards that read the same data sets. Everything working against exactly the same data sets, non-blocking, continuous.
Okay, so like Yaron said, this is a lot of nuclio functions that are enriching our data or transforming our data here. So we have functions that are triggering the location, which we're capturing what part of the city it's in. You see that we have the global car alerts. Whoever was asking about what happens when there's a warning. There's the global car events that we're triggering there. And then, as part of earlier in the discussion, there's always some storage that you might want to pass all of this, the results of your triggers. And so, what we're doing here is taking some of this enriched data from Nuclio and storing it in our data storage platform, iguazio. And so, iguazio is a platform that allows us to store multiple formats of data. All types in one location and expose it in many different formats. So we can stream data in, out, expose it as a file system, we can expose it as objects, or what have you. So what we're doing in part of the Nuclio triggers are sending into storage as well. And so what that allows you to do is to now go into iguazio, which we can now act on our data through Spark, a Spark API. I think that's one of the APIs that we support. So now you see that we're capturing some of this car's data. So every now and then we're dropping the state from Nuclio of the cars into our data store iguazio, and now we're running just a simple Spark job on it just to check out the current cars in the state of every car that has an alarm going on at the moment. So here I am at Zeppelin. If I run this function really quickly, you'll see that the data has updated from what it was previously. We can keep on clicking that data. Sorry for the resolution here. But now you're seeing that the numbers are changing as well.
So this is real-time data. So what the function is ingested, Spark sees exactly the real-time view of this segment, not a pipeline, no delays.
Right, and just, just to further the bit, is that for those more familiar with the SQL interface, Spark, we're able to expose SQL to Spark in our framework here, and it's doing this exact same function, but just in a prettier format. There we go. So only one part has an alarm going on at the moment. But as I keep on refreshing, this is what you're seeing as we are enriching our data coming in, and I'm now querying the data that I have coming into my system through Spark itself.
Yeah, and I think the last point is the dashboard that you've shown. The dashboard is looking exactly the same, the dashboard is looking at exactly the same data set in real time. So we have the first generating data. Some of the data is real time, is not the, like alerts. I don't need to wait to know that there is an alert. Some of the jobs that we show is like fuel estimates and some other estimates are machine learning Spark jobs that take this data set and just add columns with additional enriched information, and those could be delayed. We don't have to have the information about a fuel prediction in the same real-time data, but alerts may be something that we want to know immediately. So this notion now that you have a data, structured data mostly, and a bunch of functions that work around it like fees and dashboard, those dashboards read directly from the data. They don't go through any mediation. Because we also support DynamoDB API like Amazon. And so this Angular client just goes and reads the same data from the same database. And now you have, if you think about Hadoop, it's always pipeline. You take something, convert it, etc. Maybe 2 hours later you get some response. Here it's all in less than 1 second delay from input to output.
What is the source of this data?
This is emulated data that we work with some customer. And, we have another demo which is similar. Probably we're going to have next week. But also it's simulated data from automotive companies, from ride-hailing companies, that we get data sets. Okay, any questions or? Okay, was that simple? Any questions? serverless. What we do for the weather. Yes.
Yeah, so I was thinking about how, the scaling this out with like a broad team of users. Like, do you have anything in place for sort of like master function management to prevent like duplication of work and like redundant functions and things of that nature?
So part of the thing that it's a good segue to my next piece is that we're actually doing now a hackathon starts next week for a month, and we already have a bank of like 10 functions. And part of this hackathon, which will have some serious judges there from the industry, is to essentially create this sort of marketplace for app for functions, because I've shown you the sentiment analysis function. If you need to do sentiment analysis, why bother and write some? You'll have a library. So I'm looking for sentiment analysis. I can download, just modify, saying TensorFlow, image classification, etc. So you take a working thing, change the models, change the imports, and you have a new thing. And if you guys will contribute, then we'll have a bigger bank. And you see, it's really simple. I also wrote a couple of those functions, and you go to Google, you find some logic, and you frame it into these functions, and you have a working flow. You don't need to install Docker, no Docker files, none of that. Yes.
You mentioned that this could potentially also run on smaller platforms like Raspberry Pi.
Yep.
So what kind of realistic throughput or performance can you expect for edge processing?
So the way that it works, if it's a Go function, it's an inline call. If it's Python or Node or some other, there's other like real-time tricks. It's like essentially taking like PyPy and wrap it into the Go and C library. So it's generating small footprint, especially if you're writing in Go. It's about 20 megabyte footprint per function, roughly. If you're starting to import lots of stuff, probably more. But the basic function would be like 20 megabytes. And Go is extremely fast. You see 400,000 events on an Amazon VM. Okay, so on Raspberry Pi, you won't get 400,000 events, but you probably don't need 400,000.
You don't need.
Yeah, but essentially, if you run another serverless framework like Lambda, Greengrass, it's going to eat your CPU.
Yeah.
This one is binary coded. It actually, you don't have to use a Docker container. You do minus something there in the CLI. It actually generates a binary, and you can run the binary. Yep. More questions? And you have, by the way, architecture. It does cross-compiling, which is really easy. So you can specify that your architecture is ARM and build it on a powerful PC, and then the artifact will be ARM compliant. We want to do like Android APK that will actually have a listener on the Raspberry Pi, and it will immediately do the publishing into Raspberry Pi. More question?
Yeah. Amazon has CloudFormation service just to build everything you need for your service infrastructure, everything. I see you always edit, deploy, etc. the function from the UI. Do you have something like that?
Yeah. So it's part of the challenge with Amazon is Lambda. If you play with it, and I did quite a bit. On my laptop. It's very complex. The event sources, the triggers, the API gateways, all that. So it works differently. You have a YAML file that describes everything. The build dependencies, the event trigger, the API, pretty much if you work with serverless.com, the framework. So it's similar to that. So you describe the YAML file, and actually this YAML file is compliant with the Kubernetes format. So if you have Kubernetes, then you can push a function as a kubectl create with the file. It will automatically create functions for you. So you can create one file that deals with backend, like Redis or whatever, and the function in a single instruction.
Okay, I see. How do you
secrets and all that?
Yeah, it's
everything in a single. And there is an example. You'll see, you go to function definition, you'll see that it has an example with all the different.
Okay, thank you. Different question. How do you control the number of Lambda functions executed in parallel?
So there is a minimum and maximum value that you can fill.
I can control myself.
Yeah, it's part of this YAML file, optional feature.
Okay.
Say minimum and maximum.
Okay.
So maybe you want to start with 5 because you want to be ready for.
As far as I know, Amazon does not have this ability.
Yes, I have those arguments with them on a regular basis. The functions don't necessarily have to start from 0 because for certain SLA and stream processing, you may want to have the function live. And what people do today in Amazon, because they know that after 5 minutes the function goes down, then they ping the function every 4 minutes. And they calculate it's only a couple of thousand events per month, so it doesn't cost me much.
Okay.
At the point they'll probably shut down this option, but right now people are hanging around.
What about reuse resources? I mean, if may I be sure that my function is executed always on the same instance, so I can initialize resources only once and then reuse it.
Yeah, so, again, I didn't go into all the details. Maybe we need to do a bigger webinar and all that.
Okay.
But when you build in the CLI, you have a build command and you have deploy command. They're completely separate. When you push deploy, you build and deploy. So you can do a build, it generates the artifact, and then when you do the deploy, you can say deploy in 5 days or deploy again. So you don't have to repeat the build process.
So the function executed always on the one instance? Or?
No, you could have 5. So that's what I'm saying.
5.
You can create
Okay.
it creates a build, creates essentially a Docker image, the function. And then you say, take this function and distribute it to 10 days.
Any instance, and every time when a function triggered, it can be executed on any of the 5, right?
That's related to the event trigger. You need to say which trigger goes to which function.
I specify which trigger goes to which instance, right?
Yeah, there are 2 separate, that's what I'm saying.
Okay.
The event triggers and the functions don't necessarily, because what happens, let's assume you have an event trigger which is an HTTP or which is production spec. I may have a function which is now not production. I want to promote, so the coupling between functions and trigger is flexible. And I may promote the functions to production and then take it back to beta. So this is why you have this decoupling. Also, I think in Amazon case, where it's almost the same, with the bugs. Yeah, I tried to do that in Amazon. Yeah, it's not always working. So, any more questions? Good. So we hope that you'll participate in this hackathon and download the Slack channel. If it doesn't work, first it's still not production level, so excuse us if there are bugs. But if you write software and do software, then you have bugs. And we hope that you'll start using it. Thank you.
Thank you, Yaron Haviv. Now, feel free to come up now and talk to him. Thank you all for coming.